Bismillahirrahmanirrahim. Dear friends, in this video, we will calculate wind pressures for this structure using ASCE 716 specifications. These are the dimensions of the structure and these are our reference axes. As we can see that the longer side of the structure is parallel to y-axis while shorter side is parallel to x-axis. First, let's discuss some equations and parameters given in the specifications that we will be using to calculate wind pressures. We will be using directional procedure for our calculations that is described in the chapter 27 of the specifications. Since we have already discussed about the procedures in our previous video, so let's first see the difference between main wind force resisting system MWFRS and components and cladding CNC. Main wind force resisting system is defined as an assemblage of structural elements to provide support and stability for the overall structure. Typically, members which receive loading from two surfaces are designed to resist main wind force resisting system loading. Let's say we have a steel moment resisting frame building with metal roof and wall panels as shown in the picture. We would design the moment frames and spread footings at the base of the frames to resist main wind force resisting system loading from the lateral wind pressure on the wall panels and positive or negative wind pressures on the roof panels. Components in cladding is defined as elements of the building envelope that do not qualify as part of main wind force resisting system. Let's take the metal building again shown in the picture. The metal roof and wall panels would be considered cladding. The overhead door, walk door and window would be considered components. Also, the roof purlins and wall girts are receiving loadings from the cladding and are therefore considered components as well. The wind pressure then varies on these components in cladding based upon their respective effective wind area. Wind pressure equation. There are three different equations given for wind loads on main wind force resisting system. First equation is for enclosed or partially enclosed, rigid or flexible buildings. We will see these terms, what is enclosed, partially enclosed, open and rigid, flexible building in a bit later. So this is the wind pressure equation which can be used for the structure enclosed or partially enclosed having rigid or flexible behavior. We can see the equation, it has two terms. First term is actually for the external pressure effect and the second term is for the internal pressure effect. The second term is written here with negative sign, but practically this sum is algebraic sum. This can be understood when we see the calculations from example problems. All the parameters of the equation are defined as shown. Second equation is for open building having monoslope, pitched or trough roof. And the third equation is for the wind loads on parapet wall. Now let's talk about the velocity pressure. Wind pressure is derived from the velocity pressure which can be calculated using this equation. There are two equations. First one is for FPS units and second one is for SI units. There are many parameters in this equation which are defined here. Let's see these one by one. Velocity pressure exposure coefficient Kz. Kz is dependent on two things. One is the height at which wind is being calculated and other is wind exposure of the site at which the structure is located or is to be located. Kz value can be picked from the table shown. Now let's discuss about the exposure category. Exposure B is defined as the site at which buildings and structures are closely spaced as shown in the picture. Exposure C is defined as the site at which buildings and structures are very far away like open terrain as shown in the picture. Exposure D is defined as the site at which buildings and structures which are distant less than 2 kilometers from the seashore line. This K factor is calculated against each level from Z is equals to 0 to Z is equals to H. H is the mean roof height. Kz at z is equals to h is denoted by kh. For example, in this frame, kz at 15 feet, kz at 25 feet and kz at 35 feet. So kz at 35 feet is equals to kh. One thing which is important is that from z is equals to 0 to 15 feet or 4.6 meter, kz is same. For example, in this frame, story 1 is at z is equals to 10 feet and z is equals to 15 feet is in between story 1 and 2. So two separate kz values are to be calculated for story 2. Kz can be computed using these equations as well. In these equations there are zg and alpha. Both can be picked from the table shown against exposure category. The second parameter is topographic factor kzt. Kzt factor is calculated using this equation. This equation has three multipliers which can be picked from the table or calculated using equation shown. Third parameter is the wind directionality factor kd. Kd factor is dependent upon the structure type on which wind load is being calculated. Its value can be picked from the table shown. Fourth parameter is the ground elevation factor Ke. Ke factor is dependent upon the elevation of ground, that is Zg, above sea level. Its value can be picked from the table or can be computed using the equation shown. From this table we can see that as the ground elevation increases above the sea level, the wind effect is reduced. So that's why we have to calculate Ke factor, but on the conservative side the designer uses Ke factor as 1, means he does not reduce the pressure. Fifth parameter is wind speed V. In ASCE 716 specifications, different wind maps are given for different locations. We can pick wind speed from these maps if our structural location is in those maps, or otherwise we can search it on Google as well. Let's discuss about the velocity pressure equation in old version of ASCE 7 specifications. In old version, means ASCE 7-05 or earlier, we can see that the equation for velocity pressure has some additional parameter, that is importance factor I, and this I factor is dependent upon the occupancy category of the structure. Both the I factor and occupancy category can be picked from the table shown. But in ASCE 716 specifications, this I factor effect is already incorporated in the wind maps given in the specification. But if we are not picking wind velocity from these maps, then we have to incorporate this I factor in velocity pressure equation as shown in this equation. Gust factor G. As we all know, the governing equation of the structural analysis is F is equals to Ku, which defines as more the stiffness of the structure, more it will capture the forces. So wind pressure is highly dependent upon the stiffness of the structure. If the structure is stiff, rigid, then it will experience wind pressure that will be different than that if the structure is flexible. This effect can be captured using gust factor. The specification gave equations of gust factor for both type of structures. On a conservative side, designer considered the structure as rigid and take G is equals to 0.85. External pressure coefficient Cp. We have discussed the concept of external and internal pressure of wind in video 1 of this series. If you did not watch that video, then it is necessary to watch that first, as we have discussed many basic concepts regarding wind loadings. External wind pressure coefficient Cp is calculated for walls and roof using separate tables as shown. In the table for wall pressure, Cp is dependent on type of wall and length over breadth ratio, while in the table for roof pressure, Cp is dependent on wind direction, roof slope and H over L ratio. In this table, we can see that with some value of Cp, there is superscript B written. In notes, it is mentioned that these values can be reduced by a factor using reduction factors given in the table based on the area of the structure. Internal pressure coefficient GCPI. Internal pressure coefficient is not only denoted by CPI, but it is completely denoted by GCPI. Actually, gust effect factor is incorporated in this factor, which can be picked from the table shown. This factor is dependent upon the enclosure classification of the structure. There are two values of this factor. One is positive and one is negative. Because internal pressure can be positive or negative, as we have discussed this concept in previous video. Before getting started, if you are new to our channel, then please hit like and subscribe button and share as well with your friends. And let's learn structural engineering together. One more thing, we have already started design courses related to reinforced concrete structures and steel structures along with the steel connection design. If you did not watch those videos, then please go and watch those. Links of these videos I am sharing in the description below. So let's get started. So now let's get back to our example problem and see what are we supposed to do so in that particular problem. So here is the design data and we are supposed to find out the wind pressure on this particular building having wind velocity of 130 miles per hour. Building exposure C. The building is considered as rigid, so gust effect factor should be taken as 0.85. Building category is 2 and building is located on homogeneous topography. Alright. To understand the wind direction easily, we will take the help of cardinal directions. Means north, south, east and west directions. We can see that north-south line is parallel to y-axis and east-west line is parallel to x-axis. These cardinal directions will be easy to useful for the wind load reversal cases. So let's go for solution. Step 1 is to find out the velocity pressure using this particular equation. So for this equation we require these factors Kz, Kzt, Kd and Ke factors. So for Kz factor, using this particular table, since the roof mean height of our structure is 15 feet, so we will go into the table for 15 feet and we are having the building exposure as C, so the Kz value is 0.85. Now for Kzt factor, we can use this particular equation, but we are using Kzt as 1 since it is mentioned in the problem that building is located on the homogeneous topography, so it is better to take its value as 1. For Kd factor, using this particular table, as we are calculating the wind pressure on our building main wind force resisting system, so we can take the value of Kd as 0.85. For Ke factor, since in the problem statement there is no data regarding the elevation of the site ground of this building, so we can conservatively take in Ke factor as 1. So these are the factors that we have picked up from the tables. So after plugging all the values in the above equation, we get Kz is equals to 31.3 psf. Since it is only a single story flat roof building, so H means the mean roof height is equals to Z, which is 15 feet. So Q subscript H is also 31.3 psf. Remember these values, it is helpful when we are calculating the final wind pressures. Now the second step is to find out the internal pressure coefficient GCPI using this particular table. In this table, we can see that there are 4 enclosure classifications and it is defined in the second column, criteria for enclosure classification. Since our building has no opening shown in the picture and the opening area is denoted by A0 and whole surfaces area is denoted by AG, gross area of the surfaces. Since there is no opening, so A0 is 0. For the definition of enclosed building, it is said that A0 is less than the smaller of 0.01 of AG or 4 square foot. So our building is classified as enclosed by this definition. So internal pressure intensity is moderate and internal pressure coefficient GCPI value is plus minus 0.18. Now the step 3 is to find out the external pressure coefficient. Note that L is length parallel to wind direction considered. and B is length perpendicular to wind direction considered. So this is the table for finding out the CP value for walls. For wind direction from west to east or east to west, length over breadth ratio is 0.5. As length is 30 feet, which is parallel to the wind direction, and B is 60 feet, which is perpendicular to the wind direction. For wind direction north to south or south to north, it is the inverse of the previous one, which is 2. So CP value against windward wall is 0.8 because it is not dependent upon the length over breadth ratio. In the last column, we can see that it is written use with. So this CP value for windward wall will be used with QZ. In our case, QZ and QH are equal, but it may not necessary to be equal all the time. So that is why it is mentioned here that for windward wall, use QZ. CP value for side walls is minus 0.7 because CP value for side wall is also not dependent upon length over breadth ratio. Alright. Now for leeward walls, CP value for wind west to east or east to west is minus 0.5, and for the other direction CP value is minus 0.3. Now for CP value for roofs, we have to use this particular table. We can see that in this table there are two segments, windward roof or leeward roof. As we are having the flat roof, so it is nothing to do with the windward or leeward portion. We can see that in this table CP value is dependent upon wind directions, H over L ratio, and the roof angles. For wind west to east or east to west, H over L is 0.5. H means mean roof height and length is 30, which is parallel to the wind direction. So H over L is 0.5. So finding out the H over L, since it is written here that wind direction normal to ridge for theta greater than or equal to 10, but our theta means roof slope is 0. So we cannot use the upper portion of the table, rather we will use this particular portion. Alright. So we will have to look into the lower portion of the table where it is written normal to ridge for theta less than 10 and parallel to ridge. Since we are having no ridge in the building, so our H over L value is 0.5. So we will look into that particular thing. Now there is written some ranges, horizontal distance from the windward edge. So let me tell you this. When wind is blowing from this particular direction, so there are certain regions which receives different intensities of pressure, wind pressures. The region which is closest to the windward edge will receive greater wind pressure when the distance from the windward side to the region is greater, then the wind pressure reduces. So it is written here from 0 to H by 2, the CP value to calculate the external wind pressure will for case number 1 is minus 0.9. Similarly for H by 2 to H is also minus 0.9. Now for H to 2H is minus 0.5 and for greater than 2H is minus 0.3. H is roof mean height. Alright, so the complete building will be divided into these 4 regions depending upon the mean roof height. Alright, now the second case CP, all values are same, minus 0.18. So it is not dependent upon the regions. So CP values are listed here. Now for other wind direction, H over L is 0.25. So it is also the same values. Why? Because when H over L is less than or equal to 0.5, we'll have to take these values, and we are already taking that. The fourth step is to calculate the design wind pressure using this particular equation, where the first part or the first term is for external wind pressure and the second term is for the internal wind pressure. For windward walls, QZ is 31.3 times 0.85 G times CP 0.8. Remember, windward CP is 0.8 minus QH is also QZ and GCPI is plus minus 0.18. So the expression becomes this, where the external wind pressure is 21.3 and internal wind pressure is plus or minus 5.6, because we have already discussed this particular concept that internal wind pressure may be plus or minus. Now for side walls, similar calculations, and for the leeward wall, it is dependent upon the wind directions. Remember that coefficients. So this is for the east to west or west to east, and this is for the other direction. Now for the roof, note that wind coefficients calculated are same for roof at both the directions, because H over L is less than 0.5, remember. So for case 1, from region 0 to H by 2 and H by 2 to H, because in both the regions there is CP value which is minus 0.9. So here is the calculation. For region H by 2 to H, here is the calculation, and for region greater than 2H, here is the calculation. Alright. For case 2, for all the regions, there is the pressure. Now, how to combine these particular wind pressures, because when wind is blowing, then all surfaces, either the windward, leeward, side walls, roofs, all the surfaces are getting the wind pressure or capturing the wind pressure simultaneously. So how to combine these particular cases? So generally wind has case 1. Why? Because in the roof part there are two cases. So case 1 having positive GPI or negative GPI. Alright. Similarly, case 2 having positive GCPI and negative GCPI. For a particular wind direction, how many cases? Wind case 1 positive GCPI, this is the load case 1, and wind case 1 negative GCPI, this is the load case 2. Similarly, wind case 2 positive GCPI, this is the load case 3, and wind case 2 negative GCPI is the load case 4. This is for a general wind directions. And how many directions are we having? 4 directions. How? Let's take a look this. Wind for west to east, there is a case 1 with the positive GCPI, and there is a case 1 for negative GCPI. So there are 2 load cases here. Similarly, for case 2, there are 2 load cases here as well. Similarly, for all wind directions from east to west, there are 4 cases as well. So there are total 8 up till now. For wind direction north to south, there are 4 cases. So there are 12 up till here. And for south to north, there are 4 more cases. So there are total 16 wind cases that has to be defined in the analysis software, whatever we are using, to find out the stresses, combined stresses due to gravity loads and the wind loads or earthquake loads. Let's see the graphical representation of the wind pressures that we have calculated for all the load cases. This is our plan view of the building. For load case 1, when wind is blowing from west to east direction, for case 1 with the negative GCPI. This is the windward wall pressure, this one is the leeward wall pressure, and these are the side wall pressures. We found the pressures in parts, means external wind pressure and internal wind pressure separately. So previously we have written, for example, 21.3 plus minus 5.6. So now we are looking for case 1, which is having positive GCPI. So we are taking the positive part of the internal pressure. We can see that all these pressures are having the positive value of internal pressure. When we cut a section AA, then it shows like this, and the roof pressures region wise is here. Note that there are only 2 regions, but we have studied actually 4. Why? Because 0 to h by 2 and h by 2 to h, there are same coefficients, minus 0.9. So this is the one region, and from h to 2h. Since this building width is 30 feet and our mean roof height is 15 feet, so 2h will become 30 feet. So greater than 2h does not apply at this particular section. So that's why it has only 2 regions. And we can see that in 0 to h, the pressure is greater than the other region. When we cut a section BB, so this is the section view, and these are the side wall pressures and roof pressures region wise. Here we can see that all 3 regions can be seen, and pressure gradually decreases. For load case 2, when wind is blowing in the same direction for case 1, but with the negative GCPI now. Here is the windward pressure, here is the leeward pressure, and here are the side wall pressures. Note that now this time internal wind pressure is taken as negative in all these pressures. So calculate it accordingly. And see the section view. These are the pressures, alright, and section BB, these are the pressures. Okay. Now for the load case 3, when wind is blowing from the same direction but with the case 2 and with the positive GCPI. Here is the windward pressures, here is the leeward pressure, here are the side walls pressure. There is nothing difference in the wall pressures for load case 1 and 3. But where is the difference? In the roof pressures. See the section AA. The roof pressure is same for all the regions, as second case CP value is minus 0.18. Section BB also have the same pressure throughout the building, right? Now for load case 4, wind is blowing in the same direction for case 2 with the negative GCPI. These are the pressures. This is same as load case 2. The only difference in the roof pressures. And this time also the same throughout the building width, same as in section B. Now for load case 5, now this time wind is blowing from east to west. This means that it's a case for the load reversal. Wind is blowing from east to west for case 1 with the positive GCPI. Now this time this wall becomes the windward wall and this wall becomes the leeward wall. Side walls remain same. These are the pressure values. When we cut a section AA, then the shuffling of windward and leeward walls. And now this time 0 to H region is starting from the right side. For section B, same goes here. Load case 6 with the negative GCPI. Section B. Now for load case 7, wind is blowing in the same direction with case 2 positive GCPI. Nothing difference in the windward and leeward and side walls, same as that of load case 5, but here is the difference in the roof pressures. Likewise in the section B. Now load case 8 with the negative GCPI. Now for load case 9, wind is blowing from south to north. For case 1 with the positive GCPI. So this time now this wall becomes the windward wall and there is a pressure. And this wall becomes the leeward wall and here is the pressure. And these walls are now the side walls. When we cut a section, so these are the side wall pressures now and the roof pressures region wise. Section B. Alright. For load case 10 with the negative GCPI. Section A. Section B. For load case 11, same wind direction but with the case 2 positive GCPI. Only the difference here in the roof pressures. Section A and section B. For load case 12, then with the negative GCPI. For load case 13, wind is blowing from north to south now for case 1 with the positive GCPI. So this wall becomes now windward wall and this one is the leeward wall. These are the side wall pressures. When we cut a section, then these are the side walls and the starting and now from 0 to end, the region 0 to edge is starting from the right side. So section B as well. For load case 14 with the negative GCPI. Section A and B, region wise. For load case 15, case 2 with the positive GCPI, the only difference is in the roof pressures. And the last load case 16 with the same wind direction but with case 2 and negative GCPI. So this ends of our example problem 1. I have taken the simple structure in this example so that I can explain the things more clearly. Later on we will add a video to our analysis and design playlist to show how to design and assign these loads in analysis softwares. Further, in the next videos of this playlist, we will see different structures for calculating wind load pressures. I hope that through this example, you people get better understanding of calculating wind loads using ASCE 7 specifications. If you liked our video, then please hit like and subscribe button and share as well with your friends. And you can comment below for your desired content or video. I will try to make that content for you. So this is up for today. See you in the next video.